Now we're going to switch gears and talk about optical fibers. In an optical fiber, light rays of different angles can propagate simultaneously. A light ray propagating down the center of the tube would be the theta equals 0 ray, and a ray depicted here might be theta equals 15. The number of allowed rays or modes in the fiber is ultimately determined by properties of the fiber, such as its radius and its core and cladding materials. When using optical fibers with materials, i.e. films and stacks of films, we have two options of how to place them on the fiber. The first is to cleave the fiber, exposing its core, and then to deposit the materials flush to the cleaved end face. This configuration I like to refer to as axial, and it's also referred to as the dip and read configuration because devices built on it are generally dipped into samples like probes. Alternatively, we can burn or chemically etch a region of the cladding, exposing the core, in which case the stack is deposited concentrically along an exposed region. And when you do that, the rays can interact, depending on the length of that film, multiple times. So the optical properties of this so-called transversal configuration are very sensitive to the length of this stripped region. I've opened PAME in the default setting, so I just open it from a terminal. And by default, it has it's configured for an optical fiber in the axial configuration. So we're going to take this, the axial end face, and if you look at what's happening, by default we have light rays incoming from glass, i.e. from the fiber. They interact flush with a layer of nanoparticles with no protein coatings in a matrix of water, and then the solvent is a semi-infinite matrix of water. This is the default setting of the stack. You see the substrate is glass, the solvent is water, and the middle layer is nanoparticles in water. Let's go ahead and make sure the shell is set to 0. So these are bare nanoparticles. And we can take our wavelengths between 400 and 700. Now the substrate, whereas last time it was a glass slide, is now a fiber. You can see that the fiber, as I've drawn before, is also rendered here, and we would be putting our film flush on this end face. The configuration is already set to axial. For angle averaging, let's leave this as equal. This is more relevant in the transversal configuration. We also can choose if we want to look at only the S or P polarized light channels, or if we want to look at 50% S, 50% P, which is generally known as unpolarized light. We can also specify the range of angles that are allowed in the fiber. Now, when you buy an optical fiber, usually its numerical aperture is specified by the manufacturer. The numerical aperture gives the upper limit of the supported angles in this fiber. So for example, if a manufacturer reported a numerical aperture of 0.5, that means the critical angle of the fiber is 30 degrees, which means all angles incident on the fiber less than 30 degrees can propagate down the fiber. The numerical aperture is determined by properties of the fiber, including its core and cladding materials and its size. We'll use 0.275 because these are the fibers, the numerical aperture of the fibers that we use in the lab, which gives me a critical angle of 15.96. Now that's just the recommended value. In the simulation, you can set the angle range to anything you want. We also have to specify the core radius and the core diameter, but that's only so PAME can give predictions of the number of particles that would fit on the fiber, i.e. how many nanoparticles can fit on the fiber. These parameters aren't actually related to the angles. So let's look at all the angles from 0 to 15.96, and we'll increment by 1. So that'll give us about 15 different modes to consider. Let's come to the surface coverage and start this at 0 nanoparticles. Oh, now we don't want to look at the reflection amplitude, we want to look at the reflectance. So this is the reflectance off of this end face coming backwards when there are no nanoparticles and you only have an interface of glass to water. Why are there so many lines here? Well, these correspond to the angles that I specified. So clearly the number of angles will affect the reflectance. Now I want to average these. For a reflectance fiber, every single mode in the fiber eventually terminates on the interface. That's not true for the transversal configuration because an oblique angle is more likely to bounce several times, whereas a sharp angle will just propagate right through. And so the averaging changes pretty drastically between the axial and the transversal configuration, and that's what these different angle averaging parameters correspond to. Now we can see what happens to the reflectance as the nanoparticle concentration increases. So when the fiber is covered by 2.5% nanoparticles, we see that the reflectance has a dip. This is interesting because if you recall from the glass slide in air, the reflectance always had a peak. The transmission through the fiber, if one were monitoring the transmitted light, also has a dip. This is commonly reported in optical biosensors based on transmission configurations. But let's focus on the reflection. As we increase the coverage to 5%, the dip deepens. We can go all the way up to 15%, and we get this strange profile. Let's look at all of the angles again and see if we can figure out what's happening. It turns out that there is a characteristic inflection in the reflectance from the optical fiber. At low coverages, the end face mostly absorbs light. This means that as light is propagating down the fiber, it's absorbed by the nanoparticles, and so less of it is reflected. However, when the nanoparticles fill up the film density, they act more as a reflective mirror, and in that case, the reflectance actually increases. And the turnaround point at when the signal goes from mostly absorbing to mostly scattering for particles of this size is at about 11 or 12%. If we take the disk coverage all the way up to 20%, we'll see that it's mostly increasing. And this is more obvious in a simulation, and so in the next tutorial we're going to focus on simulations.